So we'll look at compact subsets of Rn. This is one of the most important results, tells us what subsets of Rn is compact in this kind, in general topology, in fact, what's called the Hynaboral Theorem. And also we'll get other consequences of compactness free with this. Okay, so here is the following theorem. Both sides of these are useful. In fact, the consequence we'll see is of the easier half after this. But the harder half is what tells you things are compact. So then you could have consequences of that. Okay, a subset, let's call it just K in Rn, is compact if and only if K is closed and bounded. Okay. So let's first see, suppose K is compact. Well, we have two things to show, but the more difficult, which is closed, we have already shown. K is closed as Rn is Hausdorff. We saw that a compact subset of a Hausdorff space is closed. How about K is bounded? This is quite easy but nicely illustrates how to use compactness. K is bounded. Well, K has an open cover by K intersection the ball around the origin of radius n. Okay, n is in natural numbers. So we take the various balls around the origin of radius n, they form an open cover. As this has a finite subcover, okay, rather, let me just say, so this has an open cover and K is compact, which must have a finite subcover. K intersection some ball of radius, ball around I1 of, ball around 0 of radius, I1, etc. E, that was horrible notation. You look at the intersection of KB0 of Ni, let's say, I equals 1 to m. So there's finitely many radii such that this happens. Now you just take the maximum, right? If n equals maximum of n1 and m, then K is contained in ball of radius 0, ball around 0 of radius n. 0 is the origin here, hence is bounded. So this is a typical way in which compactness is used. Okay, so conversely, we will base ourselves on a certain lemma, but first we'll reduce to this lemma. If K is bounded and closed, okay, then K is a closed subset of, well, minus mm, where m is the bound, m, for some m greater than 0. So we have some cube. So this is a cube of diameter 2m. Okay. Hence, K is compact by a certain lemma, the following lemma. And what is the following lemma? Well, we'll show these cubes are compact. And so closed subset of a compact set is compact, and hence we are done. Okay, so this is the lemma. Let's call it something like that. C sub d be a cube of diameter D in R space, not arbitrary space, it has to be in Rn. Then D is compact. Note these things will use Rn significantly. For instance, even infinite dimensional vector spaces, the corresponding result is not true in general. So let D be a cube of diameter, let CD be a cube of diameter D in Rn. Let's, in the pictures, I'll just take R2. What we'll do is just keep breaking up the cube, okay, into smaller and smaller cubes. And eventually, we'll use the fact that if they come down to a point. Okay, so more precisely, let U alpha in A be an open cover of CD. Okay. So if C has no finite subcover, CD has, let's call this U. Oops. If let's call this script U. So if U has no finite subcover, then we'll break it into 4 cubes, or in general 2 cubes. Then one of the 2 to the n cubes of diameter diameter D by 2 into which CD is broken has no finite subcover. Okay, so far so good. What do? Is we iterate. Iterating, we get a sequence of cubes CD C0, let's say, which is CD, containing C1, containing this, containing Cn, etc., with diameter of Cn, at nth stage. Maybe n is a bad choice because n was our dimension of diameter of Cm is going to be equal to 2 to the power of minus m, and with no Cm, having a finite subcover. By which I mean you could do one of two things, and their equivalent: either intersect U alpha with the Cm, that's an open cover of Cm, or simply ask whether there are finitely many sets which include Cm. Okay. So now what we'll do is we'll pick xi in Ci. Okay. Then what we see is that xi, the sequence xi, is Cauchy, and so this is Rn. Hence, so this is convergent. This is because after a given time, you are inside a subset of diameter 2 to the power of minus capital N. And if you take after capital N steps, and so any 2 points inside this, later points are inside even further cubes. So this is a nested sequence. So you are always very close to yourself. So you are Cauchy, and hence you are convergent. Okay. So hence convergent, say, to x, say. Okay, let's call it x infinity. But what happens is that x infinity is in an open set based on U alpha naught for some alpha naught. Or maybe I'll call it alpha infinity for consistency. Alpha infinity in A. So what happens though is that x infinity is in alpha, so that's maybe this point, but that U is open. Okay, so as U alpha infinity is open, C m is contained in U alpha infinity for m large enough. So this is a contradiction. Okay, so the idea is basically you successively bisect. If you have an open cover and there is no finite subcover, you bisect this. If all these 4 regions or 2 to the n regions had finite subcovers, they together form a finite subcover. So at least one of these regions does not. Iterate this process, break it up into 2 to the n regions, and you're getting squares of smaller and smaller diameters. Okay, and each of them allegedly has no finite subcover from U alpha. But their intersection is actually going to be a single point. We don't need to prove that. What we do is we take points in each of these, and they're all after a point inside a small cube, after some stage in some small cube. And hence this is a Cauchy sequence. It converges to some special point at infinity. This is contained in an open set. So the ball around this is contained in here. But your sets are having smaller and smaller diameters, and they all contain x infinity. Okay. So we conclude that actually at some stage you had a open cover with a finite subcover having just one set U alpha infinity, which is your contradiction. So this is the key result, the Hynaboral theorem, which tells you that, well, this is the earlier result, that any closed and bounded subset of a Euclidean space is compact, and conversely. So now an immediate consequence is the following theorem. Okay, that if f maps x to R and x is compact, then f is bounded and attains its maximum. And minimum, I can say, if I'll save myself writing a couple of words by saying minimum. It's almost the same proof. Okay. Firstly, f of x is contained in R, is compact, hence bounded, which means that is f is bounded. A function being bounded is exactly the same as its image being bounded. The definitions just coincide. Okay, so this is compact. So as I said, it's the easier half which gave it. Further, y are maxima attained, namely if y is supremum of f of x, x in x, okay, then y is in f of x closure. This is by definition because we have a point on the real line. Oh, so this is also equal to supremum of y in f of x in the image set. So if I have to call it something else, y max, then I'll say y max. That's because if I have this point y max here, by definition of supremum, there are points arbitrarily close to this. So the supremum is in the closure. We have seen this once before. Okay, but f of, we know the image is closed. Hence, y max is actually in the image. So this tells you that the supremum is actually attained, and so there is a maximum point. And similarly, using the infimum, which by the way, because of boundedness sup and in for both finite numbers, they are attained. So the usual proof for in analysis is you can upgrade from boundedness directly, but this is a more topological way of looking at things.